Oh no. So 8.1, we are just going to skip it. You can always do it and show me. That's perfectly fine. But I think it makes perfect sense for us to destroy this 10-mark question, which is really a monster. Yes, over to you, Elsie.
An eggshell, oh, wait. An eggshell contains calcium carbonate and impurities. An excess amount of a standard dilute acetic acid solution of concentration 0.5 moles per cubic decimeter and volume 250 centimeters cubed is allowed to react completely with an eggshell of mass 56 grams. The equation of the reaction is given by the balanced equation shown below. The acetic acid that remained unreacted is neutralized by 25 centimeters cubed of sodium hydroxide with a concentration of 0.968 moles per cubic decimeter. The equation for the reaction is given by the balanced equation below.
Right. Thank you so much, Elsie. So this problem is actually what is known as a back titration. So what is a back titration? It's when originally you were reacting two reactants, and one of those reactants is actually remaining, and that reactant is an acid. Then you say, well, I don't want this acid to remain. So you take that remaining acid and you react it with another reactant in order to finish up the unreacted acid. So that's a back titration. Well, let's talk. They say an eggshell contains calcium carbonate and impurities. An excess amount of a standard dilute acetic acid solution of a concentration of 0.5 mole per cubic decimeter and a volume of 250 cubic centimeters is allowed to react completely with an eggshell having a mass of 56 grams. Okay. The equation for the reaction is given by the balanced equation below. Now, the acetic acid that remained unreacted is neutralized by 25 cubic centimeters of sodium hydroxide having a concentration of 0.968 mole per cubic decimeter. And this is the balanced equation for that reaction as well. Well, that's awesome. Now, already we can see that hydrochloric acid, acetic acid. Hey, this thing of being used to working with hydrochloric acid. But yes, we can see that the acetic acid is in excess. Well, that's fine, which means that calcium carbonate is the limiting reagent. Because as soon as it's finished, the reaction will stop. And then we'll take this remaining acid and react it with sodium hydroxide. But what is the question asking from us? The question says, calculate the percentage of calcium carbonate in the eggshell. It's still the same as calculate the percentage purity of calcium carbonate in the eggshell. We already know the mass of the eggshell, that is 56 grams. We just need to know the mass of calcium carbonate. All right? And we are not really given anything that can assist us to find the mass directly. And we also know that we can't use the number of moles of hydrochloric acid that we can get from 0.5 mole per cubic decimeter and this volume of 250. Why? Because the acid is in excess. So what we need to do here actually is to determine the number of moles that reacted with calcium carbonate, the number of moles of the acid. So this is what I want you to see. What is that? I want you to realize that the number of moles that are available for this acetic acid, we are going to get them by using this 0.5 and the 250 cubic centimeters. That's how we get the number of moles that are available. But then the number of moles in excess of the acid, we are going to get them by using the information about sodium hydroxide. Then if we know the number of moles that are available at the start, and we also know those that are in excess, then we can actually find the number of moles that reacted with calcium carbonate, or those that are used to react with calcium carbonate. So let's go ahead and do that. So we'll begin by finding those that are available at the start of the reaction for the acetic acid. And for that, we'll define concentration. We say, well, the concentration is defined as the number of moles divided by the volume. And the concentration is given to us as 0.5. That's nice. We are looking for the number of moles, but the volume of the acid is given as 250 cubic centimeters. That is an incorrect unit. So we have to divide by 1,000 and effectively get 0.25. Take it to the correct unit. Then now it's time for us to cross multiply so that we can find the number of moles of acetic acid. But of course, we understand that these are the number of moles that are available at the start of the reaction. So when we cross multiply here, we simply get 0.125 moles. Now we go to sodium carbonate. We define sodium hydroxide, Yes, it's sodium hydroxide. We define its concentration. Once again, it is defined as the number of moles divided by the volume, all right? Then we say, well, the concentration of sodium hydroxide is 0.968, and the volume of sodium hydroxide is 25 cubic centimeters, which if we divide by 1,000 will give us 0.025. And if we now cross multiply, well, we simply get 0.0242, and then we say moles. But then if we study this chemical reaction, we can see that the mole ratio is 1:1 between acetic acid and sodium hydroxide, which means that the number of moles of acetic acid, which are in excess, right, is actually equal to the number of moles of sodium hydroxide, which is simply 0.0242 moles. So now we know the moles in excess, and we also know the available number of moles. And you remember that the number of moles in excess is equal to those that are available minus those that are used or those that reacted. What we are looking for is those that are used. So you can take your used to the left-hand side and take your excess to the right-hand side. Then you'll find that the number of moles of acetic acid that reacted or that were used to react with calcium carbonate will simply be what? Those that are available, which is 0.125, minus those that are in excess, which is 0.0242. And if you now press this into your nice and beautiful calculator, you get 0.1008 moles. So these are the number of moles that reacted with calcium carbonate. But then you're not going to use them as they are because they are not really in a ratio of 1:1. It is a 2:1 ratio. So that's what you're going to tell us. You tell us that the relationship between acetic acid and calcium carbonate is a 2:1 ratio. Now we want to know if I have 0.1008 moles of acetic acid, then how many moles do I need for calcium carbonate? Well, I actually need half of that. You also don't need to write a ratio like this, honestly. You could have just said the number of moles of calcium carbonate is half the number of moles of acetic acid. It's still acceptable as well. So whichever one you prefer is perfectly fine. Right. Then if you now divide this by 2, you find that the number of moles of calcium carbonate will simply be 0.0504 moles. So now you know the moles, then you just need to find the mass. So you know that the moles are defined as the mass divided by the molar mass. And what is the molar mass of calcium carbonate? We actually determined in the previous one that it's 100. And if we now cross multiply, well, you simply get a mass of 5.04 grams. This is the mass of calcium carbonate. Well, now that you know the mass of calcium carbonate, then you can now find the percentage of calcium carbonate in this 56-gram sample. It's the same as finding the percentage purity, really. There's not much of a difference, no? So if you now go to your calculator and you plug in everything, you find that the percentage of calcium carbonate is actually exactly 9% when you plug it in. Yes. So it seemed as if it's an awful lot of work. Well, it is an awful lot of work, but then it was a back titration. So it's still another way of the limiting reagent, the excess reagent, just that you are now given this in two different reactions. So yes, if we can be able to identify which one is going to give me the available number of moles and which one is going to give me those that are in excess, then you know how to find those that are used by using this formula. So it's a free 10 marks if you ask me.